Hello, everybody, and welcome to another wonderful day of PChem. So today we're going to begin Chapter 8 by finally getting to take our quantum mechanical principles and actually apply them to atomic systems. So we're finally going to study electrons again. So we're going to specifically focus in on a well-known set of systems called hydrogenic atoms. So what a hydrogenic atom is we simply take an atom and we surround it by a single electron. And this is a nice, simple case to study, mostly because we don't have to deal with the pesky nature of two very small, fast electrons interacting with each other. But can simply focus in on how an electron moves around a nuclei. So one of the real important early discoveries in quantum mechanics is that the electron moved around a nuclei in discrete orbitals. And one of the proofs of this was essentially atomic absorption of a photon, where we can predict where a photon will absorb based on the orbital that the electron is being excited from and to, using the difference of the inverse squares of these two orbitals, along with an empirically determined parameter. It was possible to figure out exactly where we'd expect to see an absorption signal from an electron around a simple hydrogenic atom. So in the case of hydrogen, what we found is that there are several different series where you'll expect to see these excitations. So the first of which is essentially called the Lyman series, where we excite from the core electron. So this is where n is as close as it can be. So n is 1. Then the more commonly known Balmer series, where we start from an n equals 2 electron to n equals 3, 4, and 5, and so forth. And these form essentially the visible spectrum of a hydrogen atom, where the lowest energy species goes from 2 to 3, then 2 to 4, 2 to 5, and then they begin to converge in the near UV. And then similarly, we have the Pascan and bracket from the n equals 3 and n equals 4 starting orbitals as well. And so one of the important things about this is it dictated that we do indeed have electrons moving around an atom in discrete energy levels, where there's only a single set of energy levels that we can expect the electrons to move in. Now, the real trick is going to be developing a good Hamiltonian and wave function that can describe these systems. Because as we've seen before in our other quantum mechanical systems, as soon as I have a Hamiltonian in hand, I can usually derive a wave function. And with the wave function, I can get any quantum mechanical property I would like. This ranges from momentum, angular momentum, location, so on and so forth. So we know basically how kinetic movement of a hydrogenic atom will behave. So the real trick is going to be describing the potential field for a hydrogenic atom. So what we can do is say if I've got a single electron, it's going to feel a static potential from the nuclei, which is going to be based on the average distance from the system. So what we can do is make use of Coulombic electronic reactions. So we're going to see a potential that's going to go as Z, where this is essentially the charge or the number of protons on the nuclei, times, of course, the charge of the electron, where I'm going to have a positive charge on the electron and a positive charge on the electron, a negative charge, positive charge on the nuclei, on the proton, negative charge on the electron. Z gives me the number of protons, and then this negative attractive term means that they have, again, different charges. So this will be a attractive potential that will grow with the number of protons existing on the nuclei. However, we also have to deal with how these two charges interact. And this is first going to be controlled by this 4 pi term, essentially representing the spherical nature and movement of the electrons, because they can exist in full 3 dimensions. So this is where the 4 pi comes in. Then we also have what's called the vacuum permittivity. So this essentially dictates how well charge transmits in an existing media. And not too surprising, the media inside a nuclei is a vacuum, as there's nothing in existence in between the electron and the nucleus. So this is going to have a permittivity that is fairly well known. The last and almost most important term here is R. So this is essentially going to be the radial distance of the electron from the nuclei. And one of the big things that we tend to find here is the further away the electron is from the nuclei, the less attracted it is or pulled in by this potential term. And this becomes very important because this R term also dictates that we're also shows a dependency on the radial term, which unfortunately is going to give us some slight issues with trying to develop a potential, because we have a potential that is variant with radii. And we know how to deal with systems where radii is fixed, but this is going to be a little bit more tricky. Not to mention, in addition to this potential, we have to deal with the fact that we also have a little bit of a more tricky the kinetic energy than we're used to. Because now our kinetic energy involves two separate components. It turns out that in addition to the electronic movement that we typically think of, we also have movement of a nuclei. So the kinetic energy of the electron is actually going to be a fairly familiar basic form, where it's going to be based on the negative of h bar squared times twice the mass of the electron times essentially the second derivative, or the Laplacian, of the electronic position. So again, this is going to be the second derivative with respect to all coordinates of the electronic position. So this is going to be our classic second derivative with regards to the radii, but also with regards to theta and phi. So we've got this pesky issue of a full unrestricted radial movement, which isn't something we've quite had to deal with before. But in addition to this, we also have the kinetic energy of the nuclei, which will be addressed with a very similar Hamiltonian, where instead we're going to be looking at the mass of the nuclei in addition to the Laplacian of the nuclear components. So this gives us more or less three components to our Hamiltonian. We've got the kinetic energy of the electrons, kinetic energy of the nuclei, and the potential well that the nuclei generates for the electrons. So it's going to try and pull these electrons in, while the kinetic energy is going to want the electrons to keep moving. So we can then substitute in each of our terms, and we have a more general expression for our Hamiltonian. However, one of the things that is worth noting is that it turns out with our big, heavy nuclei and a fairly slow change in the second, and a fairly small second derivative for the nuclear components, we can actually treat the nuclei as being relatively static. And this makes sense. Compared to the electrons, they are going to be very slow moving, and as a consequence have fairly low kinetic energy, even despite their greater mass. So we're going to typically drop this second term towards zero. And this produces a relatively general Hamiltonian for a hydrogenic system. So this is going to be the Hamiltonian for a system where we only have a single electron, where we're going to be focusing in on the kinetic energy of the electron and the potential energy of the electron. So this leaves us with a little pesky trick we have to deal with. We now have to somehow combine the second derivative of electronic position with a radial term. And we know, due to Heisenberg's uncertainty and commutation, that these two are not going to end up playing well together. Not to mention, we also have the fact that I can break down my Laplacian into a radial set of terms and a angular set of terms, which we did previously when examining a rigid rotor. So previously we got very lucky and that we could set the derivatives with respect to r equal to 0. Here we're not so lucky. But one of the things that is worth noting is that you're going to notice we have a lot of dependencies on position here. So two derivatives with respect to r and two r-based terms. But it turns out we only have a single expression, and this is our Legendrian, which has a dependence upon angular motion. So what we're going to be doing over the next couple lectures is we're going to be separating our Hamiltonian out into radial components. So this is going to be everything that depends on r, and the angular components. So we're going to have to focus a little bit more on that pesky Legendrian. And once we do this, we're going to be able to break our wave function apart into an angular and radial components. So this is a classic trick that we used with the three-dimensional box, and we're going to use a lot more here in the future, taking a complicated wave function and splitting it into simpler solvable portions. So we're going to be talking a little bit more about this separability of the wave function next time. Till then, take care.